This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy. We go deep and lightly surface the big ideas.
I want you to picture something for me. If you can, just close your eyes for a second. Imagine you're standing on the edge of a cliff.
Okay.
Not a scary cliff, just a high one, maybe overlooking the ocean. And there's a storm rolling in.
You can feel it.
You can feel that weird pressure in your ears. The wind is whipping your hair around. And you can see those, those dark, bruised-looking clouds churning way out in the distance.
It's a very visceral experience.
It is. But here's what I'm thinking about when I stand there. I'm looking at that water, just smashing against the rocks, spraying everywhere. I'm looking at leaves swirling in these chaotic little tornadoes. And I get this sinking feeling that, I don't know, that it's just too much.
Too much information.
Exactly. I mean, we have supercomputers.
Sure.
We have satellites. We have AI that can write poetry, for crying out loud.
We do.
But if I ask the world's most powerful computer to tell me exactly where that one specific leaf is going to be in, say, 10 minutes, or exactly how that one wave is going to break, it can't do it. And that drives me crazy. Why? Why is nature so much smarter than our machines?
Well, you've just walked right into the single biggest headache in the history of physics. You were describing turbulence.
Right.
You're describing chaos. And the reason our computers, even the massive ones at Google or NASA, choke on that storm is because of something called the butterfly effect.
Okay, I know the pop culture version of this, Ashton Kutcher movies and all that.
Right.
A butterfly flaps its wings in Brazil, and 3 weeks later, there's a tornado in Texas.
It sounds like a metaphor, but, mathematically, it's a horror story.
A horror story.
An absolute nightmare. It means that the systems we are trying to predict, like the weather, or blood flowing through a heart valve, or plasma in a fusion reactor, they're hypersensitive.
Okay.
If you get the starting conditions wrong by even a microscopic amount, I'm talking the position of a single molecule, your prediction for the future doesn't just get a little bit wrong.
It's not just off by a bit.
No, it falls apart completely.
So if my computer thinks the wind speed is, 10.0 miles per hour, but it's actually 10.0000001.
Then you fast forward 2 weeks, and your computer says sunny day, while reality says Category 5 hurricane.
Yep.
That's the wall we've been banging our heads against for decades. We call it nonlinearity.
And usually the story ends there. It's too hard. We give up. Nature wins.
Usually. That is the story, yeah.
But not today. Because we've got a stack of research here, specifically a brand new paper out of the University of Maryland, MIT, and IBM, that says we might have finally found a way to punch a hole in that wall.
A pretty big hole.
But, this is a big but, the solution sounds completely insane.
It really, really does.
The paper is titled Quantum Simulation of a Noisy Classical Nonlinear Dynamics. It's up on their Access now.
It's a mouthful.
It's a mouthful, but the gist of it,
Yeah.
to solve these impossible, messy, chaotic storms, they didn't try to clean up the math. They made it messier.
They did.
They looked at noise, static, interference, the stuff we spend billions of dollars trying to eliminate. And they said, you know what? Let's add more of that.
It is one of the most counterintuitive leaps in computational physics I have seen in a long, long time.
So that's our mission today. We're going deep into this paper. We're going to track the journey of this research team, Jinpeng Liu, Herman I. Colden, Hari Crovey, Nuno Loureiro, Constantino Trevisa, and Andrew Childs.
A really incredible team.
We're going to find out why they hit a dead end back in 2021 and how this crazy idea of weaponizing noise allowed them to simulate things we thought were basically uncomputable.
We're going to talk about the villain of the story in nonlinearity. We're going to talk about the breakthrough, and we're going to talk about why this proves, maybe for the first time, that quantum computers aren't just faster calculators.
Right.
They're a fundamentally different way of seeing the world.
So buckle up. It's going to get bumpy. Let's start with the bad guy. Section 1, the villain. You threw this word around earlier. Nonlinear.
I did.
And I feel like people use that word at dinner parties to sound smart, but what does it actually mean? Why is it the enemy?
Okay, so to understand the enemy, you have to understand its friend. And the friend is linearity.
Linearity.
Linearity is safe, it's comfortable, it's the logic of input equals output.
Give me an example.
Okay, imagine a block of wood on a frictionless table. If I push it with 1 pound of force, it moves at a certain speed.
Right.
If I push it with 2 pounds, so double the force, it moves at double the speed.
Kegel, proportional.
Exactly. It's predictable.
Mhm.
If you make a small mistake in how hard you push, you get a small mistake in how fast it goes. The error stays proportional.
The world makes sense.
The world makes sense. Now, nonlinearity is where that proportionality dies.
Okay.
In a nonlinear system, the output is not proportional to the input. The input might be squared or cubed, or it might feed back into itself.
So I push the block a little bit harder, and instead of going a little bit faster, it explodes?
Or it flies off the table, or it turns into a pigeon. I mean, not literally, but mathematically, yes. In a nonlinear system, a tiny change in input can trigger a massive, disproportionate change in output.
Right.
The source material uses the classic analogy of the inverted pendulum.
The inverted pendulum. This is like trying to balance a broomstick on your hand.
Exactly. Imagine a rigid stick with a heavy weight on top. You're trying to balance it upright on the tip of your finger.
I can feel the anxiety already.
Right. Now, mathematically, there is a perfect spot. If you get it absolutely vertical, 90.0000 degrees, on and on forever, and there's absolutely no wind, and your hand is perfectly still, it will stay there forever.
In theory.
In theory, that's a fixed point. But in reality...
In reality, my hand shakes. I breathe. A truck drives by outside.
Right. Those are perturbations, tiny little nudges.
Mm.
Now, if this were a linear system, like a regular pendulum just hanging down...
Or like a grandfather clock.
Like a grandfather clock, yeah. Those nudges wouldn't matter much. It would just wiggle a bit and settle back down. But because it's inverted, because it's unstable and nonlinear, what happens to those tiny nudges?
I get bigger.
They get amplified, the stick starts to fall, and here's the kicker. The way it falls. Does it fall left? Does it fall right? Does it spin? That depends entirely on the microscopic details of that first tiny nudge.
The sensitivity to initial conditions.
Precisely. Now, imagine trying to simulate that on a computer, a classical computer.
Okay, I'm a computer. I have a model of the broomstick.
But you're a computer with finite memory. You can't store infinite decimal places. You have to round off numbers.
Sure.
So maybe you store the position as 90.00000000 with Ds, but the real position was 90.00000002.
So I have a tiny error. A rounding error.
In a linear system, who cares? But in this nonlinear system, that error gets amplified. Then you calculate the next second, and the error gets squared. Then cubed. You iterate this 1,000,000 times for a weather simulation, and suddenly...
Suddenly my simulation says the broomstick fell left.
Yeah.
But in reality, it fell right.
Exactly. Your prediction is worthless. You aren't simulating reality anymore. You're just simulating your own rounding errors.
And that's why we can't predict the weather past 2 weeks.
That's it. The chaos amplifies our ignorance faster than we can calculate.
And this isn't just about broomsticks. This is the math that governs
No.
everything that
Everything that flows. The Navier-Stokes equations.
Oh, the big scary ones.
The big scary ones. These are the equations that describe how fluids move. Water in a pipe, air over a wing, the atmosphere of Jupiter. To simulate these directly, specifically the turbulence, you have to track the fluid at every single scale simultaneously.
From the big massive jet stream down to the tiny little molecular swirls.
Yes. And we measure this difficulty with something called the Reynolds number. It's basically a score of how turbulent the fluid is.
Good.
For our atmosphere, the Reynolds number is something like 10 to the 8th.
10 to the 8th. That's 100 million.
100 million. And as of 2020, the absolute best state-of-the-art supercomputer simulations could only handle Reynolds numbers of about 10 to the 4th.
Wait. 10 to the 4 is 10,000? The reality is 100 million.
We are orders of magnitude off. We are bringing a knife to a nuclear war.
Wow. That's depressing.
It is the computational wall. And this brings us right to the team behind this paper, Lou, Childs, and their colleagues. They have been staring at this wall for years.
So they aren't new to this fight.
Oh, no. In fact, they published a paper back in 2021. It was a big deal at the time.
I remember seeing some headlines about it.
Right. They proposed a quantum algorithm to solve these differential equations. They thought they had it.
But
There was a catch. There's always a catch. Their 2021 method worked, but only for weak nonlinearity.
weak nonlinearity.
Yeah.
That sounds like diet chaos.
Basically, it worked as long as the Reynolds number was low, as long as the flow was thick and gooey and
Yeah.
calm, like honey. But the second you got into strong nonlinearity, the real turbulence, the stuff we actually care about, their algorithm just fell apart.
So they built a storm simulator that only works when it's sunny.
Harsh, but
Yeah.
yeah, pretty accurate. And the only other option on the table at the time, a method by researchers Layton and Osborne, could handle the chaos but it had its own fatal flaw.
Which was?
Its runtime scaled exponentially with time.
Explain that to me. Exponential scaling with time.
It means if you want to simulate 1 second of turbulence, maybe it takes a minute.
Okay.
If you want to simulate 2 seconds, it takes an hour. 3 seconds, a year. 4 seconds.
The heat death of the universe.
You're not far off. So it was mathematically possible, but practically useless.
Okay, so it was a total dead end.
Correct. So that was the deadlock. You have the 2021 Liu method, which is fast but can't handle storms, and the Leighton Osborne method, which handles storms but takes forever. They were stuck.
This is where the story gets good. Because usually when you hit a wall like that, you try to drill through it. You try to make your math more precise.
Right. You try to find a better way to track those particles. You try to fix the error.
But they didn't do that.
Mm-hmm.
And this brings us to section 2. The breakthrough. What was the aha moment here?
They stopped trying to fix the error. They decided to embrace it.
What does that mean?
They shifted their whole framework from what are called ordinary differential equations, or ODEs, to stochastic differential equations, SDEs.
Stochastic. That just means random.
It means involving a random variable, yeah. The shift in perspective here is profound. They looked at that inverted pendulum and they said, why are we failing?
Okay.
We are failing because we are obsessed with knowing the exact trajectory of the stick.
Which is impossible because of the chaos.
Right, so they asked a different question. Instead of asking, where is the stick, they asked, where is the stick likely to be?
Okay, so they moved from tracking the particle itself to tracking the probability cloud around the particle.
Yes. But they went a step further, and this is the part that twists my brain a little. To make this probability tracking work, they didn't just accept that the world is noisy.
They did what?
They artificially added noise to the math.
Whoa, stop. Stop. You're telling me they looked at a math problem that was too hard because it was too sensitive, and their solution was to shake the table?
Yes, that's a perfect analogy. They shook the table.
That sounds like giving up. That sounds like me saying, I can't hear the music clearly, so I'm going to turn on a vacuum cleaner. How does adding more noise help you solve a problem?
It sounds backward, I know, but go back to the pendulum on your finger.
Okay, I'm balancing it. It's wobbling.
If you are trying to keep it perfectly mathematically still, you are fighting a losing battle against every tiny perturbation. The system is hypersensitive.
Right.
It discriminates, in the language of the paper, between 0.000001 degrees left and 0.000001 degrees right.
Sure. Those tiny differences become huge.
But now imagine you're standing on a vibrating platform. The whole room is shaking.
Mm-hmm.
Does it matter anymore if your finger is 0.0001 degrees off?
No, because the vibration of the room is way bigger than that tiny error. The error gets lost in the noise.
Exactly. The noise swamps the fine details. By adding noise, you wash out the microscopic sensitivity that was causing the computational explosion in the first place. The system becomes less sensitive to small changes.
So by shaking the table, you stop caring about the microscopic stuff.
You blur the picture. Think of it like a super high-resolution photo of a crowd. If you try to track every single pixel, every pore on every face, your computer just crashes. It's too much data.
Right.
But if you blur the image slightly...
I can still see the crowd. I can see, oh, the crowd is moving towards the exit.
Exactly. You lose the individual pores, the specific trajectory of a single particle, but you gain a clear, computable picture of the average movement. You trade precision for stability.
That is wild. So they are simulating a version of reality that is purposefully blurry.
And here's the kicker. The paper argues that this blurry version is actually a better model of the real world anyway.
How so?
Because the real world is noisy. Real fluids, real weather, real markets. They're full of thermal noise and random vibrations and quantum fluctuations.
So the perfect noiseless equation was actually the fake one all along. We were chasing a ghost.
In a sense, yes. We were chasing a phantom of mathematical perfection that doesn't actually exist in nature.
Okay, conceptually, I am with you. This is blowing my mind, but I'm with you. We add noise to stop the chaos from exploding.
Right.
We look for the average behavior, not the specific path.
Right.
But talk is cheap. How do you actually do this? How do you take a messy, noisy equation and shove it into a quantum computer?
Okay, this is section 3, the mechanics. And this is where the math gets incredibly elegant.
And complicated.
A little complicated, yeah. Oh, we'll break it down. We need to move from tracking particles to tracking waves.
Okay, particles to waves.
Remember, we aren't asking where is the particle anymore. We're asking how does the probability distribution, the wave of possibilities, change over time? To do this, they use a tool called the Kolmogorov equation. Specifically, the backward Kolmogorov equation.
That sounds like a spy novel. The Kolmogorov identity.
It does, but it's actually a transformation tool. It's a mathematical lens. It takes the nonlinear problem, the chaotic, messy broomstick, and turns it into a linear partial differential equation.
Wait, you said the magic word, linear.
I did.
Linear means easy. Linear means input equals output. No more explosions.
Precisely. The Kolmogorov equation linearizes the chaos, but there is a price.
There's always a price.
Yeah.
What did we have to pay to get this linearity?
Dimensions. We moved from a simple three-dimensional problem, x, y, z, into an infinite-dimensional space of functions.
So we made the math easier, but we made the sandbox infinitely big.
Correct. And a classical computer hates infinite dimensions. It chokes on them. But do you know what kind of computer loves high-dimensional vector spaces?
Let me guess. A quantum computer.
Bingo. Quantum computers live in what's called Hilbert space. They are native to these vast, complex environments. So the team had to figure out how to map this fluid dynamics problem onto the qubits of a quantum computer.
How do you map water flowing in a pipe to qubits on a chip? That seems like a huge leap.
It is. They used a method called Kárlman linearization, or sometimes called Koopman methods, but let's simplify it. They mapped the classical variables onto quantum harmonic oscillators.
Flashback to Physics 101. Masses on springs. Boing, boing.
Conceptually, yes. But in quantum mechanics, the harmonic oscillator is the fundamental container of energy. It's not a physical spring. It's a mathematical ladder.
A ladder.
Yeah, an energy ladder. And you have operators, little instruction sets that climb this ladder.
Instructions like what?
Like the creation operator, which is written as a dagger. It adds a unit of energy. It puts a marble in the bucket.
Okay, a dagger adds a marble.
And the annihilation operator, which takes a marble out.
So they took the speed of the water, the pressure, the viscosity, and they translated it into a language of add a marble, remove a marble.
Essentially, yes. They encoded the physical reality into these quantum operators, and this allowed them to write down the Hamiltonian.
The Hamiltonian, that's the master equation, right? The recipe that tells the system how to evolve over time.
Yes. And in their paper, this Hamiltonian has a very specific structure. It looks like minus A plus B plus C.
Minus A plus B plus C. This sounds like alphabet soup. Let's make this real. If I am a water molecule in a storm, what is A doing to me?
A is the anchor. A represents the noise and the dissipation.
Dissipation like friction.
Exactly, it's the friction. It involves the term a dagger A, which just counts the marbles. It's stable. It's the force trying to calm the storm down.
Okay, so A is the chill factor. It's the viscosity saying, hey, slow down. What about B and C?
B and C are the chaotic part, specifically C. C is the villain we talked about earlier.
But the troublemaker. The nonlinearity.
That's the one. C represents the nonlinearity. In fluid dynamics, this is a term called advection.
Advection.
It's the part of the flow that transports the flow itself. It's a bit weird, but imagine you're running on a treadmill.
Okay.
But the faster you run, the faster the treadmill speeds up because you are running.
That sounds like a recipe for face planting.
That is advection. It's a feedback loop. And mathematically, this term is cubic. It involves three operators multiplied together like a dagger A. It amplifies energy wildly.
So it's the engine of the chaos.
It is.
Yeah.
And technically, it is unbounded.
Unbounded means it can go to infinity.
It means the energy can theoretically shoot up forever. And this is a huge problem. You can't put infinity into a computer, even a quantum one.
So A is trying to calm things down, C is trying to blow things up to infinity. It's a battle. How do you stop the computer from melting?
This is section 4. Taming the infinite. They used a very clever trick called regularization.
Which is fancy talk for.
Cutting it off. Truncation.
To just deleted the infinity.
They set a ceiling. They argued that in a physical system with friction, remember A, our anchor,
The calming force.
the super high energy stuff, the infinitesimally small swirls and eddies, it gets killed off by friction very, very quickly. It just dissipates into heat.
So the tiny ripples die out before they can wreck the whole ocean.
Exactly. So they defined what they call a low dissipation subspace. They picked a cutoff number, let's call it K. They said, we are only going to simulate the interactions that happen below this energy level K. Anything above K, we ignore.
But isn't that cheating? I mean, if you ignore part of the math, isn't your answer just wrong?
It introduces an error, yes. But and this is the core of their mathematical proof, a really critical theorem. They proved that as you increase that cutoff K, as you make the ceiling higher and higher, the answer you get converges to the true solution.
So if you make the ceiling high enough, the error becomes practically invisible.
Correct. And crucially, the cost of raising that ceiling, the amount of extra computer power you need, only scales polynomially.
Polynomially, that is the magic word, isn't it?
It is the golden ticket. It means if you want double the precision, you maybe do 4 times the work, not 1,000,000,000 times the work, like with the exponential scaling. It makes the problem solvable in the real world.
Okay, so let's recap where we are. We have taken a chaotic storm.
Yep.
We added noise to it to blur it so it doesn't explode.
Right.
We translated that blurry storm into a language of quantum marbles on an energy ladder.
The harmonic oscillators, yes.
We chopped off the infinite, really high energy parts that would break the computer. Now we run the machine, the qubits dance, the simulation finishes.
Right.
Now we need the answer.
And we arrive at section 5, the readout, and what we call the observation problem.
Right. Because in quantum mechanics, you can't just look at the answer. It's not like a file on your desktop.
No, if you look at a quantum state, you collapse it. You destroy the complex probability cloud you just spent all that time building. All that rich information is gone.
So how do we get the expected value, the average behavior of the storm, out of the box without breaking the box?
They use a very clever technique involving a readout state, which they write as Brossi out.
Okay.
They essentially measure the overlap between their final simulation state and this special readout state.
Okay.
It connects back to things called Hermite polynomials.
Okay, math words.
It connects back to probability shapes. It's a way of asking the final quantum state, hey, what's your average value for this specific thing I care about? But you're the detective here. Did you spot the catch in the paper?
I did. I was waiting for this.
Yeah.
Section 5.3, exponential scaling with inverse relative error. That sounds scary again. I thought we got rid of the exponential monsters.
We got rid of them for the time evolution. We can simulate 1,000,000 years of weather efficiently. But the readout, the actual act of getting the answer, has a bottleneck.
And what is the bottleneck?
The initial noise. Remember how we started this whole thing by adding noise at the beginning?
Yeah, to shake the table and make it stable.
The math says you cannot let that initial noise be 0.
What happens if I try to be perfect? What happens if I say, my system is perfect, the noise is 0?
The readout time goes to infinity. The algorithm explodes.
Seriously.
Seriously. The term in the equation is 1 over sigma, where sigma is the amount of noise. If sigma is 0, you're dividing by 0. Boom.
That's fascinating. It's like the computer saying, I can tell you the future, but only if you admit you don't know the present perfectly.
That is a profound way to put it. The algorithm requires uncertainty. It demands humility. If you try to be a god and know the initial state with infinite precision, the quantum computer just refuses to work.
But if I admit, okay, I'm a human, my measurements are fuzzy, there's a little bit of noise, then it works.
Then it works. And since in the real world, our measurements are always fuzzy.
It works for us.
Exactly.
Okay, so the theory holds up. The philosophy is beautiful. But does it work? Did they actually simulate a fluid, or is this just fancy scribbles on a whiteboard?
Section 6, the proving ground. They ran a benchmark. They took the Navier-Stokes equations and applied them to a specific test case called the Taylor-Green vortex.
The Taylor-Green vortex. Sounds like a sci-fi weapon.
It's a classic test in fluid dynamics. Imagine a fluid trapped in a box with periodic boundaries. So it's basically a donut shape, a torus.
Okay.
And you have these swirls, eddies, and vortices spinning in opposite directions. It's complex, it's chaotic, but we happen to know the analytical solution for it under certain conditions.
So they have an answer key. They can check their work.
Right. And they ran 2 cases. Case 1, vanishing noise. They turned the noise dial way, way down, almost to 0. The quantum algorithm matched the true solution perfectly. The flow fields they plotted in the paper were identical.
Check plus. What about case 2?
Case 2, high noise. They cranked up the interference. Now, in this case, the physics actually changes. The noise pushes the fluid around in new ways. The average flow is different from the calm flow.
Right. The vacuum cleaner is on now, so the music sounds different.
Perfect. And did the quantum computer catch that?
Did it?
It nailed it. It matched the ensemble mean of 10,000 classical brute force simulations.
Wait. So to check the quantum computer's single answer, they had to run a classical computer 10,000 times and average the results.
Basically. That shows you the power difference right there. The quantum computer did in one run what the classical computer needed 10,000 runs to approximate.
That is the quantum advantage right there, in a nutshell.
And they backed this up with a heavy theoretical proof. They proved this simulation problem is BQP complete.
BQP complete. I've seen this term. It's like the the final boss of quantum computing problems.
It stands for bounded error quantum polynomial time. To say a problem is BQP complete means it is one of the hardest problems a quantum computer can solve.
Okay.
It implies that if a classical computer could solve this efficiently, it could simulate any quantum computer.
And since we're 99.9% sure classical computers can't do that.
It means this problem is fundamentally out of reach for classical machines. It's not just about speed, it's about the fundamental structure of the computation.
That's a mic drop moment.
It is. It really is.
But before we pop the champagne, we have to look at the fine print. Section 7. This isn't a magic wand for everything, is it? There are some rules.
No, it's not. The paper is very clear about the specific constraints. First, the system must be divergence-free.
Divergence-free. In English.
Incompressible. Like water. You can't squeeze it into a smaller space.
So this wouldn't work for, say, a gas.
Well, it wouldn't work if you're trying to simulate a shock wave or a supersonic jet engine where air gets compressed. For that, this specific algorithm might need some significant tweaks.
Okay. Constraint number 2.
It must be dissipative.
We talked about this. Energy has to leave the system eventually.
Right, friction, viscosity. If you have a system where energy just keeps building up forever, like a perfect laser in a perfect box of mirrors without an outlet, the math blows up.
And number 3.
Sparsity. The interactions need to be somewhat local. You can't have every particle interacting with every other particle in the universe simultaneously. Luckily, most physical systems are like this.
Okay, so it's not a theory of everything, but for fluids, for weather.
For fluids, for weather, for some areas of finance, it's huge.
Let's talk about that. So what? Why should I, the listener, care about this paper beyond it being a really cool piece of math?
Look at the author's own speculation in the introduction. They talk about meteorology.
Weather forecasting.
We mentioned that Reynolds number of 10 to the 8.
100 million?
The atmospheric boundary layer. That's the air right above the ground where we live, where crops grow, where wind turbines spin. It's incredibly turbulent. We currently can't simulate it accurately. We just guess at it with rough models.
So this could mean actually accurate storm tracking, knowing exactly where the tornado will touch down, not just which county it's in.
Potentially. It could mean climate models that don't just guess at cloud formation, but actually simulate the fundamental physics of the clouds. That would be revolutionary.
That saves lives. That changes economies.
It absolutely does. Then there's finance.
Of course. Follow the money.
The stock market is a nonlinear, noisy system. It's what's called a nonlinear Markov process.
Millions of people buying and selling based on news, panic, greed.
Yeah.
That's the noise.
Exactly. Current models are pretty good at normal days, but they struggle with the fat tails, the sudden crashes, the unexpected booms. This approach, which embraces the noise, could model those risks much, much better.
Though I'm a little terrified of a hedge fund with a working quantum computer.
Offices.
A valid concern, to be sure.
You know, as we wrap this up, I keep coming back to the philosophy of this whole thing.
Go on.
We spent the last 50 years of the computer age obsessed with precision. More bits, higher resolution, perfect logic. We thought that if we could just get enough precision, we could predict the future.
The old clockwork universe theory from Laplace.
Right. And then chaos theory came along and just broke that idea. It said, no, you can't. And for a long time, we just stood there staring at the broken pieces.
We saw chaos as the enemy, the thing that stopped us.
But these researchers, Liu, Colden, Crovey, and the rest of the team, they looked at the chaos and said, let's work with it. Let's make it a tool. They realized that the truth isn't in the specific trajectory of one particle. It's in the cloud. It's in the probability.
It's seeing the forest instead of getting lost, trying to count every single leaf.
That is a beautiful way to put it. By letting go of the need to be perfectly right about the little things, they found a way to be probably right about the big things.
We trade precision for truth.
Exactly.
So, a quick summary of the journey. We started with the Wall-Strong nonlinearity, the point where the butterfly effect kills classical computing.
We saw the dead end of their 2021 paper, and then the aha moment of using stochastic differential equations, of deliberately adding noise to the system.
We watched them map that noise onto quantum harmonic oscillators, the buckets of marbles, using the Kolmogorov equation to make it all linear.
They tamed the infinite energy with regularization, the cutoff, and proved that it still gives the right answer in the end.
And finally, they showed that even in a chaotic donut-shaped storm, the quantum computer could find the truth, where classical computers would just be guessing or running thousands of times to catch up.
It's a massive step forward. It's not just a new algorithm, it's a new way of thinking about how to model our messy reality.
And that is the thought I want to leave you with today. We spend so much time and energy trying to filter out the noise in our lives. We want clear signals, we want perfect plans, we want certainty, but maybe, just maybe, the noise is part of the answer. Maybe you have to take the table a little bit to see where things really settle.
Couldn't have said it better myself.
A huge thank you to the authors of this paper, Jinpeng Liu, Herman I. Colden, Hari Crovey, Nuno Loureiro, Constantina Trevisa, and Andrew Childs, and the teams at the University of Maryland, MIT, and IBM. This is heavy, dense work, but it really, really matters.
It really does.
And to you, listening, thanks for riding the turbulence with us. Keep diving deep. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other podcasts, responding to the content, and checking out our related articles at helioxpodcast.substack.com.